Okay, now we are on the last topic of topic 7, which is segmentation with deep learning. So let's begin with understanding what image segmentation is and how it differs from related tasks like classification and detection. As shown in this visual, we can think of three main levels of computer vision. First, we have image classification, where the model simply answers, is there a dog in this image? It doesn't tell us where the dog is, just whether one is exists. And next is we have object detection, where the model finds what is in the image and where is it by drawing a bounding boxes around the objects. Like this one, no? Like the dog and the cat here. And finally, so we have image segmentation, which takes it a step further by identifying exactly which pixels belong to which object. So this gives us a more detailed and fine-grained understanding of the image. So what exactly is segmentation? So it's the process of dividing an image into regions based on the pixel characteristics. This allows the model to analyze the content more precisely. Think of it as predicting the class level of every pixel in the image rather than just providing a bounding box. Segmentation is specifically useful in fields like medical imaging, autonomous driving, and satellite imagery, which detailed spatial information is crucial. Okay, so next would be um, so that we understand what segmentation is, so let's talk about how segmentation can be done. So there are many techniques out there, but here we will highlight two widely used unsupervised methods. So we have this key means and mean shift. So key-means segmentation is one of the most popular and intuitive clustering techniques. The idea is simple. So we choose a value k, which is the number of clusters we want to segment the image into, and the algorithm assigns pixels to the nearest cluster based on the features like color or spatial proximity. So then it updates the cluster centers, as you can see here. So it finds clusters, and then finally, then we have these clusters here until it converges, no? As you can see here. So, and the mean shift algorithm here, or the mean shift segmentation. So one of the well, this is more advanced, so it doesn't require use to predefine a number of clusters. So instead, it works by finding modes or high density regions into the data. Circular window here is moved toward areas of higher data density. Shown, as you can see, no? As you shown here, there is here we have a high density here. And what else? Well, this technique is effectively finding clusters based on the data distribution itself. And what else? And well, this technique is special, especially useful when the structure of the data is not known. That's why this is an unsupervised method, because you let this algorithm find what would be the best groups to be clustered. So both of these are non-deep learning methods, but they lay the groundwork for modern image segmentation techniques. And and while they are not as accurate as deep learning based approaches, they are still useful in certain applications. So especially when computational efficiency or data simplicity is key. Okay, so let's look at a practical of sample to better understand how key means can be used for segmentation. So in this case, we're using key means to segment a cat from its background. So as you can see here, we see the original input image. So it is a kitten lying on a pillow next to a green leaf, as you can see here. So this will be we need uh to the the output should be this kitty should be sleeping on the leaf. So right now in this image, so we have it is sleeping in a somewhat a bed with a blue bed here, and this one is our target background for this image. So what should we do here is, so the image is passed through the k-means algorithm, which cluster all the pixels into 5 groups. So what we have here is it collects all the dark colors here. So this was another cluster, and this one it clusters all the high valued or the white values here, and also the um in between black 0 to 255, I think. What else? The all blue color, the represents blue, and then some um some points here. Then what else? Okay, so now we cluster it. No, we have 5 clusters. So based on their color and some of the intensity features. So as you can see, it is segmented here. So now now we can manually identify which cluster corresponds to the kitten and discards the others that not represents the background. So in this case, the blue here. So once we isolate the cat clusters, so we can superimpose them into the new background. And in this case, a leaf. So resulting the final image shown here. No? So this demonstrates how key means can be used not just for understanding image structure, but also for object extraction and image manipulation in a very intuitive way. Of course, key means has limitations like being sensitive to lighting conditions, and choosing the right number of classes or a number of clusters rather. But it still provides a solid foundation for classical simulation tasks. Okay, so now there's an important limitation. So we need to understand. While techniques like key-means and min-shift are useful for simple segmentation tasks, so they struggle in real-world scenes, especially ones like this with multiple classes and clustered backgrounds. So in this image, as you can see, a typical urban street with people, vehicles, and other road markings are all packed closely together. So classical methods don't have the semantic understanding to distinguish between all these different object types. So they only group pixels based on basic similarity like color or texture. So as a result, um, overlapping or similar colored objects are often misclassified. So small or distant objects may be lost entirely, and there's no understanding of object categories like uh, distinguishing between a person and a sample, a pole in this case. So this is where the deep learning based segmentation techniques like fully convolutional networks, UNet, or mass RCNN becomes essential. So these models learn which representation of object context, shape, and meaning from data. So the takeaway here is for simple tasks, classical methods work, but for complex real world environments, we need deep learning. Okay, so in this slide helps clarify what computer vision tasks like image classification and object detections and how they differ. So here we see image recognition or classification. So in this task, so the model simply predicts what's in the image as a whole. So here it's saying there's a 60% chance it's a sheep and 30% as a dog and so on. But notice it's only giving us a single label and doesn't tell us where in the image those objects are. So in contrast, so here, so we have object detection. So this is more advanced, and the model not only identifies what objects are present, but also draws bounding boxes around each of them, and effectively telling us what and where. So if you're just classifying photos, classification is enough. But if you want to analyze complex scenes with multiple objects, especially in tasks like autonomous driving, security, or robotics. So object detection is the way to go. So this distinction also helps lay the foundation for segmentation, which is even more detailed, and we will get into that shortly. Okay, so now that we understand the difference between classification and detection, so let's go one step deeper into the world of segmentation. So this slide highlights two major types of segmentation. So what we have here is a semantic and instant segmentation. So semantic, here we are classifying each pixel in the image. So every pixel that belongs to a ship, for example, is labeled the same. But in this case, it's in blue. So it doesn't matter how many ship there are, they're all treated as one class. So this is useful for general understanding like how much of the image is grass, road, or sky. And for instance segmentation, so this is more precise. Not only not only do we classify the pixels, but we also differentiate between individual objects. So you can see each ship has a different color, meaning the model understands that these are separate instances of the same class. So this is especially important in applications like autonomous driving or medical imaging, where counting and distinguishing objects is critical. Oops. Okay, so here, um, this slide gives us more visual comparison of three key concepts: the object detection, semantic segmentation, and the instance segmentation. So as you can see in the left, so the model identifies and draws bounding boxes. And what else? So it draws bounding boxes around each detected object. However, it doesn't know the exact shape or contour of the object. So it just knows where the object is roughly located. It's useful but not very precise at the pixel level. Semantic segmentation here, in this case, the model classifies every pixel in the image, but it doesn't distinguish between different instances of the same class. So all people, for example, are shaded with the same color. Even if there are five different people, it's great for scene understanding but lacks individuality. And what we have here is the instance segmentation. So this combines best of the both worlds. It's not only classifies every pixel, but also differentiates between instances of the same class. So you can see here that each person has a different color label. So the model understands that these are distinct individuals. So, okay, here shows the same thing for chairs and semantic segmentation groups. All chairs together as one class, blue, while instance segmentation um, identifies each chair separately with unique colors. So, in short, the granularity increases as you move from object detection, semantic segmentation, and instance segmentation. With instance segmentation offering the highest level of detail and utility. Okay, next would be okay. So in this slide, we're looking at some of the most widely used deep learning models for image segmentation. So these models form the backbone of modern semantic and instance segmentation systems. So Signet is one of the earliest encoder to decoder. Let me write it down. So this one is the earliest encoder, decoder architectures, specifically designed for semantic segmentation. So semantic segmentation. So it uses convolutional layers to extract features and a decoder that unsamples them. So it's efficient in memory usage uh, because it uses pooling indices during upsampling. Well, we will just discuss it later on with more detail. And what we have here is UNet. So originally developed for this one is originally developed for biomedical image segmentation. segmentation. So unit has become a staple in segmentation tasks. It um, somehow it features semantic encoder decoder structures, same as Signet, with skip connections. But later on, we will discuss on how unit works and in more detail. And what we have here is DeepLab B3. So this is a very advanced one. Or this is a very advanced architecture that uses dilated convolutions. Later on, we will discuss it later. No? And we have mass RCNN. And this one is a trivial one because mass RCNN builds on faster RCNN. So faster RCNN. By adding the third branch that outputs segmentation mask along with the bounding box. So it will performs instant segmentation. So later on, we will discuss this up. Each of these models has its strengths depending on whether we prioritize speed, accuracy, or the complexity of the scene. So they are the foundation for tasks like medical imaging, autonomous driving, and real-time video analysis. Okay, next would be let me let me remove this one. Oops. All right. Okay, so to give you a more detailed about Signet, so um, Signet is one of the earliest and most influential deep learning models for semantic model or semantic segmentation. So Signet was developed in 2015 with a clear goal, accurate pixel level classification. So it does things using an encoder decoder architecture. So um, the encoder part is responsible for extracting features or feature representations from the input image, and its structure is based on the BGG16 mm, network, as you can see here. So this is a BGG16 um, architecture. And then, but what makes Signet special is how it performs upsampling, as you can see, this one. So in the decoder, so this is the encoder, and this one is the decoder. So instead of learning how to upsample, it uses the max pooling indices from the encoder, and this helps the model efficiently reconstruct the spatial details, which is crucial for accurate segmentation. Finally, once the full resolution feature map is obtained from the decoder, Signet applies a pixel-wise classification layer that, that assigns a class to each pixel. So resulting in the segmented output you see on the right here. So overall, Signet balances accuracy and memory efficiency, making it suitable for applications like road scene understanding in self-driving cars and medical imaging. Okay, what else? Okay, next would be okay. Okay, for UNet, so it is a very influential model in the field of image segmentation, especially in biomedical imaging. So UNet was developed in 2015 also. And what else? Unlike many earlier models, it was designed um, specifically uh, for semantic segmentation tasks. So what makes unit stand out is its symmetric encoder-decoder structure. So as you can see, often referred to as a U-shaped architecture. So this is how it represents. So which is actually where the name comes from because of its U-shaped architecture. So let's break that down. So here, so we have the contracting part, as you can see here, which which is essentially a series of convolution and pooling operation. So this part reduces the spatial dimensions of the image while capturing high level features. Then in the middle here is the bottleneck where it holds the most compressed form of the features, as you can see here, which holds most of the features information. And then, as you can see in this one, the expansive path, which does upsampling, it restores the image spatial resolution while merging it with the high resolution features from the contracting part. So as you can see here, using the skip connections. So these skip connections are key. They allow the model to retain fine-grained spatial information that would otherwise be lost. So what's the result? So the unit can make accurate pixel level predictions, even when the training data is limited. So which is why it became so popular in medical fields like tumor detection, lesion detections, where data sets are often small. Now let's talk about DeepLab V3, a powerful model developed by Google in 2017, though the DeepLab family itself started back in 2014. So DeepLab V3, let me use this one. So the DeepLab V3 is a semantic segmentation architecture, which means it focuses on labeling every pixels every pixels in image according to the object class. What sets DeepLab apart is its ability to handle objects at multiple classes or multiple scales. A common challenge is a real world. This is a common challenges in real world images. So the key innovation here is something called the Atrus convolution, as known as dilated convolution. Instead of using the standard convolution filter, um, Atrus convolution spreads out the filter weights with holes, and then or or gaps in the in between. So this allows the network to increase the receptive field of basically seeing a wider context without increasing the number of parameters uh, or computation. So as you see in this diagram, DeepLab V3 applies multiple atrus convolutions in parallel, as you can see here, what we have here, and then and then it has a different level of dilation rate. Example, we have 2, 4, 8. It depends. Then this known as this they call this the atrus spatial pyramid pooling. This one is like if you look as you can see, it's like a pyramid or they call it. the atrus spatial pyramid pooling for the ASPP. So the idea here is that the idea is to capture both local and global context. So the model can detect both small and large objects in a single forward pass. So this makes deep lab B3 extremely effective in complex scenes such as urban landscapes or indoor environments where object size vary a lot. So when we can we will explore this in our laboratory exercises later on, and to further to further dive you in and to understand it very well, because the explanation here is quite limited with regards to how the deep lab V3 really works. Okay, so we will just have to discuss it in our laboratory exercises. Okay, okay, next would be okay, the most one of the important models also is the mass RCNN. So this model was introduced in 2017 and is widely regarded as one of the most powerful frameworks in this domain. Now, what exactly does mass RCNN do? Well, it takes object detection to the next level, while models like fast RCNN just let me use this pen. Okay, okay. So while models like faster RCNN um okay, let me erase it. There's this one. Okay. Okay. So models like fast RCNN just predicting bounding boxes. So well faster um RCNN only predicts bounding boxes. And then also obviously the class labels. And mass RCNN also generates segmentation masks for each object instances. So this means we don't just know what and where an object is, we also know which exact pixels belongs to it. Here's how it works. So it starts from um, the master RCNN backbone. So as you can see here, to detect an object and what else? Detect object and their bounding boxes, of course. And then it adds an extra segmentation branch in parallel, as you can see here, which produces a pixel level mask for each detected object. So this made possible as some call the ROI align, which is improves the precision of the mask by aligning features correctly, fixing a problem in the ROI pool that we have already discussed in faster RCNN. So despite this additional functionality, so mass RCNN is well, mass RCNN is relatively simple to train and doesn't add too much computational overhead. As you can see in the image, so each person and bike in the scene is selected with its own class, and colored mask shown in its also in its shape. So that's the power of instance segmentation. So for now, this is our last topic for topic 7, and we will have a series of laboratory exercises regarding this topic 7. So stay tuned and hope for the best for you guys. So thank you for listening and see you on our laboratory exercises. Thank you.